In this lecture, we're going to talk about antiderivatives. We started this course with this idea that if you had some function, say f of x or f of t, that its derivative, f prime of t, was the rate of change of f. And we thought about examples where, for example, you know where something is at every point in time, and you want to know how quickly it's moving. Well, now we're going to think of questions in kind of the other order, where you know the rate of change of something, and you would like to reconstruct the original function. So let me just start with a definition. So we say that the function capital F of x is an antiderivative of little f if the derivative of big F is little f. And so, for example, let's say you have the function 2x and the function x squared. So we know that the derivative of x squared is 2x, and so therefore x squared is an antiderivative of 2x. Now, there's something a little bit unusual about this definition, which is the use of the word an here. It's not that x squared is the antiderivative of 2x, it's an antiderivative, which leaves open the possibility that there might be multiple antiderivatives. And in fact there are, because for example, if you take x squared plus 3, well, it's still true that the derivative of x squared plus 3 is 2x, so therefore x squared plus 3 is also an antiderivative of 2x. In general, I can add any constant to x squared and get an antiderivative of 2x. So in general, we'll say that x squared plus c is an antiderivative of 2x for any constant, or maybe I should say for all constants, c. Now, a natural question then is, are these the only antiderivatives of 2x? This gives us sort of an infinite family of functions whose derivative is 2x, so are there others? Well, it turns out that there actually aren't any others. You can show, you can sort of prove with the mean value theorem that if two functions, capital F and capital G, have have the same derivative, well then F is equal to G plus some constant on every interval. Okay, so we can kind of talk about the sort of general antiderivative of a function. So what we're going to say then, what we're going to say then is that the general antiderivative of 2x is x squared plus c. And I'm going to write that using some kind of unconventional notation for now. I'm just going to write anti of 2x is x squared plus c. Okay, so our goal is going to be to figure out how you can take the antiderivative of various functions. And so let me just run through a few quick examples here. And basically the idea for starters is that you make up an antiderivative formula by kind of taking a derivative formula and turning it backwards. So for example, the derivative of sine of x is cosine of x, which means that the general antiderivative of cosine of x is sine of x plus c. right? And again, if I wanted to write that, I like to think of taking a derivative as kind of moving from top to bottom. So the derivative of sine is cosine, and so the antiderivative of cosine is sine. Well, plus c. Here's a nice easy example. The derivative of e to the x is e to the x. Well, so that means that the antiderivative of e to the x must be e to the x. Again, plus c. Okay, how about one more? The derivative of, say, some constant times x, say like a times x, is equal to a. And so that means that the antiderivative of a constant is that same constant times x. Okay, so next time we'll look at a few more examples of antiderivatives and start to make a table of all of the simple ones that we can come up with.